Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. In my last class, I discussed the concept of pattern classification and I briefly explained the concept of the supervised learning. So today I am going to continue the same discussion. First, I will explain the concept of deep learning, how it is different from the traditional pattern recognition system. And after this, I will discuss the concept of the supervised learning and the unsupervised learning. So what is deep learning? Here you can see in my next slide. Now already I have discussed about the definition of the deep learning. Now deep learning is nothing but the subset of the machine learning. So mainly it is the extension of the artificial neural network. So in this figure you can see what I am considering. I am considering one image and I want to recognize whether it is a car or not. So in this case, in case of the deep networks, it is nothing but the cascade of nonlinear transformations. And in this case, I am considering the hierarchical model. That means I want to extract more and more information from the input signal, input image. So by considering the cascade of nonlinear transformations and also we are considering the end-to-end learning, we want to extract more and more information from the image, from the signal. That means the image has the low frequency information, the high frequency information, maybe some diagonal edges may be there. So all this information I want to extract from the image. I will explain later on about the deep learning techniques, but mainly it is a cascade of nonlinear transformations and the end-to-end learning, and we want to extract more and more information from the input image, from the input signal. And based on this we can do the classification. So the output is the car. That means it is identified that a car is present in the image. The space of machine learning methods. So I will show some popular machine learning methods in the next slides. So first you can see there are many algorithms like recurrent neural networks, convolution neural networks, autoencoders, support vector machines. SVM is the support vector machines. GMM is the Gaussian mixture model. Restricted Boltzmann machine, sparse coding, so perception. So these are the techniques, the popular techniques, and you can see the left side is the deep structure, the right side is the shallow structure. So if I consider support vector machine, that is nothing but the shallow structure. But if I consider the that convolution neural network, the recurrent neural networks, that is the deep learning techniques. And again I am classifying, you can see some techniques are supervised and some techniques are unsupervised. So if I consider I can consider the supervised neural networks. Also the unsupervised neural networks are also available, like the competitive neural networks are the unsupervised neural networks. And you can see like Gaussian mixture model, that is unsupervised. Restricted Boltzmann machine, that is also unsupervised. But support vector machine, you can see this side, that is the shallow learning. But if you consider the like the convolution neural networks, recurrent neural networks, these are the deep learning techniques. And some are the probabilistic methods. You can see if I consider a Bayes NP, deep belief networks, restricted Boltzmann machines, GMM, all these are the probabilistic method. So here in this diagram I have shown the popular machine learning algorithms. And in this case you can see I am considering the machine learning techniques. Some techniques are supervised. You can see the machine learning books, because already I told you that it is not possible to discuss all the machine learning concepts in this computer vision course. So that is why I am considering only the discussion, the brief discussion about these techniques. So one is the supervised technique. If you see maybe the regression, you can consider decision trees, random forest, and classification like the k nearest neighbor technique, trees, logistic regressions, naive Bayes, support vector machines. In case of the unsupervised clustering, I can consider the singular value decomposition, that PCA, the principal component analysis, the k-means clustering, like this we can consider. So also we have the reinforcement learning, that I will explain later on. So these are some machine learning techniques. And in case of the machine learning techniques, you can see first I have to do the training, and after the training we have to go for the testing. So here you can see I have the label data and we are considering the machine learning algorithms that is mainly for the training. So in case of the supervised technique, already I have explained, we know the class levels and the corresponding training samples are available. So based on these training samples, what we can consider, we can do the training of the system, the training of the algorithm. And after this, what we can do, that suppose the level data is available and already we have the learned model. So by using the learned model, we can do the prediction, we can do the decision making. This is about the machine learning basics. And here I have shown the concept of the supervised, unsupervised and the reinforcement learning. The reinforcement learning I will explain later on. So here you can see, first one is the classification example I have shown. So two classes I have shown, the class A and the class B. And in case of the regression, you can see it is nothing but the fitting of a line between the sample points. That concept also I will explain later on. And what is the unsupervised? Unsupervised is nothing but the clustering. So the class labels are not available and only the feature vectors are available, and based on some similarity we can do the grouping of the feature vectors. That is the clustering. And in case of the traditional pattern recognition system, input image I am considering, I can extract the features like shift I can consider, or maybe the hog feature I can consider, and after this we can apply some pattern classification techniques, maybe the unsupervised classification techniques or also the supervised classification technique we can apply for classification, for object recognition. This is about the traditional pattern recognition system. That means from the input image, from the input signal, I have to extract the features, and based on these features we can do the classification. And you can see the difference between the deep learning and the machine learning. So first, if you see, the first one is the machine learning. So I have the input image. First I have to extract the features, and after this I have to apply the classification algorithms, and based on this I can do the classification. In case of the deep learning, the feature extraction is not important, but what I am considering one network, that is the suppose artificial neural network, which can directly extract important features from the input image and simultaneously it can do the classification. So that is about the deep learning. So from the input image directly we can extract some important features, and based on these features we can go for classification. That is about the deep learning. But in case of the machine learning, first we have to extract the features, and after this we have to go for the classifications. So here you can see, in case of the deep learning, what is available here, you see, suppose this is my input image. So from the input image I can extract some information, maybe the low level information I can consider, mid level information, high level information I can consider, maybe the low frequency information, high frequency information, all the information I can extract. So first I can extract the low level parts like this, and after this I can extract the mid level parts, and finally I can extract the high level parts. So that is why it is called the deep learning, because I want to extract more and more information from the input image, and that is nothing but the cascade of nonlinear transformations, and it is the end-to-end learning I am considering. So this is the deep learning techniques, and I have shown the interpretation of the deep learning techniques. So what exactly is deep learning and why it is generally better than other methods on image, speech and certain other types of data. So deep learning means we are considering the artificial neural networks having several layers of node between input and output, and the series of layers between input and output do feature identification and processing in a series of stages, just as our brain seems to do. Multi-layer neural networks have been around for 25 years. So what is new actually, if we consider the difference between the artificial neural networks and the deep networks, you can see in case of the artificial neural networks, good algorithms are available for learning the weights in networks with one hidden layers. But if I consider more and more hidden layers with the existing algorithms which are used for the artificial neural networks, that may not be sufficient to train the artificial neural network. So that is why we have to consider the deep networks in which there are some good learning algorithms are available, so that we can train the hidden layers. And if I want to compare the deep learning versus machine learning, you can see I can show some comparisons like this. One is the data requirement. In case of the deep learning, it requires large amount of data. In case of the machine learning, we can train on lesser data, and accuracy provides high accuracy in case of the deep learning, but in case of the machine learning, accuracy is less. The training time, another parameter. For deep learning, we need the longer training time, but in case of the machine learning, takes less time to train. And hardware dependency, if I consider, requires GPU to train properly, but in case of the machine learning, it can be trained on CPU. And also the hyperparameter tuning. So in case of the deep learning, can be tuned in various different ways, but in case of the machine learning, limited tuning capabilities. And I want to show the concept of the overfitting. So first figure, you can see that in the first figure, I am placing the decision boundary between the classes. Then in this case, you can see it is not the perfect placement of the decision boundary. If I consider this decision boundary, there may be misclassification. But if I consider a second figure, that is a good compromise, so I can consider the decision boundary like this. But in the third case, what I am considering, that is the overfitting. Overfitting in the training. So if you see this diagram, if I consider the error versus these different cases, one is the inadequate, one is the good compromise, one is the overfitting. Corresponding to the underfitting, that corresponds to high bias, you can see the error is maximum during the training, and also it is maximum during the testing. But if I consider the good compromise, you can see during the training, the error is less than the underfitting case, and also in the testing, the error is less than the underfitting case. So that is this case, you can see. And in case of the overfitting, that corresponds to high variance. During the training, the error is very less. But then corresponding to this, I am getting the decision boundary between the classes. But in the testing, the error is very high. That is the overfitting. So underfitting is also not desirable, and the overfitting is also not desirable. So that is why we have to consider that case, the middle case. The middle case is the good compromise we have to consider. So that is the concept of the overfitting. And in this case, I have shown these cases. One is the regression, one is the just compromise, and another one is the overfitting corresponding to regression. Second one is the classification. Corresponding to the classification also I have shown, one is the underfitting. That means underfitting means high training error and also high bias. And the training error close to the test error. And after this, I am considering the just compromise. That is the training error slightly lower than the testing error. That is the just right. And after this, I am considering the overfitting case. So in the overfitting case, low training error, and the training error much lower than the test error, and that corresponds to high variance. And after this, I have shown the deep learning. So in the deep learning also, I have shown the training error and the testing error in all the cases. One is the underfitting, one is the just right, and one is the overfitting. So this is about the underfitting, just compromise, and the overfitting. Here also I have shown these all the cases. One is for the regression, one is for the classification. One is the underfitting and one is the overfitting, and I am considering the just right. In the middle one is the just right I am considering. Regression is nothing but the fitting of a line between the sample points. In case of the pattern recognition algorithms, the bag of algorithms that can be used to provide some intelligence to a machine. And these algorithms have a solid probabilistic framework. And for this, we are defining the classes, and also we need the features. So algorithms work on certain characteristics defining a class referred as features. And what is a feature? If I consider, suppose if I want to do the classification between these two alphabets, one is the I, capital I, another one is the small I. So this I is the pattern I can consider. So what will be the feature for this classification? One is the uppercase, another one is the lowercase. The presence of a dot in lowercase I can distinguish this I, the small I, from capital I, and it is a feature. And the feature's value can be discrete or continuous in nature. And in most of the cases, the single feature may not be sufficient for discrimination. So I may need more features for discrimination between classes. So in this case, I am giving one example, the classification of fish. So I am considering two fishes, one is the sea bass, another one is the salmon. So how to consider this classification problem? So maybe we can consider the input images we can consider, and we can extract some features. The features may be the length of the fish, the lightness of the fish, the width of the fish. Like this we can extract these features from the input image. So after getting the image, we have to do some pre-processing, image processing we have to do, and also we have to do the segmentation, the image segmentation. That is, the segmentation is important to isolate the fish from the background. So in the image we have the background and the foreground. The foreground is nothing but the fishes. So that means we have to use a segmentation algorithm to isolate fish from one another and from the background. And after this we have to extract features. So this is the technique you can see. So first I have to do the pre-processing. Input images are available. After this we have to extract features, and after this we have to do the classification. One is the salmon, another one is the sea bass. And in this case you can see I am considering only one feature. That feature is the length of the fish I am considering. And based on this I am just counting, you can see, and here you can see I can recognize salmon and the sea bass, but there are some misclassification. The misclassification is shown by the red one. That means the sea bass is recognized as salmon. Here you can see the sea bass is recognized as salmon, that is the red one. And if I consider this black one, you can see the salmon is recognized as sea bass. And you can see this is the decision boundary. If I consider, this is the decision between two fishes, one is the salmon, another one is the sea bass. But the misclassification is happening. The sea bass is recognized as salmon and salmon is recognized as sea bass. This is by considering only one feature. Next figure you can see I am considering another feature, that is the lightness of the fish I am considering, and again I am counting. So counting means I am just determining the probability. In this case also you can see there are some misclassifications. The red one is the sea bass and the black one is the salmon. The sea bass is recognized as salmon and salmon is also recognized as sea bass. So this is the misclassification is taking place because I am considering only one feature. So that is why we can consider maybe two features or maybe more features for this classification problem. So we have to minimize the misclassification. We have to increase the accuracy. So we have to reduce the number of sea bass classified as salmon, that we have to reduce. So for this we have to consider the decision theory. Well, what decision theory we can consider? You can see here. So I am considering now two features. One is the lightness of the fish, another one is the width of the fish. So that is the feature vector I am considering. X is the feature vector. And if I consider these two features, here you can see it is a two-dimensional feature space. I am considering one feature is the lightness, another feature is the width. And you can see the decision boundary between these two classes. One is the salmon, another one is the sea bass. Then in this case the classification accuracy increases because of considering two features, but in this case there are still some misclassification. You can see some misclassifications are happening in this case also. But because of these two features, the accuracy increases as compared to previous cases. And in this case, you can see for optimal performance, we have to select the best decision boundary between the classes. If I consider this decision boundary, that is the non-linear decision boundary, that classification error will be less between these two classes. The objective is dealing with novel data, and in this case we have to the performance on the training data, and that is important. First we have to do the training and we have to see the performance on the training data, and after this the performance on the new data, novel data, we have to consider. That should be good. The performance for the training and the testing should be good. So in case of the pattern recognition systems, what are the main steps? The first one is the data acquisition, that is nothing but the sensing. That is I can consider, if in case of the image classification, I have to consider image acquisition, or maybe the sensors we can consider for signal acquisition, and after this we have to do the pre-processing, and after this we have to do the segmentation and the grouping. So pattern should be well separated and should not overlap, that we have to consider. Here you can see the block diagram of the pattern recognition systems. First one is the sensing. After this we have to do the segmentations. The next step is the feature extraction, and all the features may not be discriminative, so that is why we have to go for feature selection. And after this the classification and the post processing. The post processing is nothing but the system evaluation. So we can determine accuracy, we can determine the false positive rate, the true positive rate. So all these rates we can determine, and based on this we can adjust the parameter of the system, that is nothing but the feedback. So we can just do the feedback. We can see here the next step is the feature extraction, and we have to consider the discriminative features. And one important point is the feature should be invariant to affine transformations. Like if I consider translation, rotation, scale, so in this case also the feature should be invariant to affine transformations. After extracting the discriminative features, we can go for classification, and after this the post processing, that already I have explained. So we can improve the performance. So for this we can give the feedback to all the steps like feature extraction, feature selection. So that feedback is important from the output to the inputs. So now the design cycle is, first one is the data collection, next one is the feature selection, after this the model selection, we have to do the training, and after this the evaluation of the pattern recognition system. And one important point is the computational complexity. We have to determine the computational complexity of the system, that we also, this is important. So same thing I am showing here. First one is the collection of data, after this the selection of the features, selection of the model, and after this we have to train the classifier, and after this the evaluate the classifiers. And here you can see the feedback. So I am considering the feedback so that we can improve the performance of the pattern recognition system. And what is clustering? Clustering is the unsupervised learning, and in this case you can see that we have to do the grouping, and one important point is we have to consider high inter-class similarity we have to consider, and also we have to consider the low inter-class similarity. In case of the grouping, this is very important. One is the high intra-class similarity, another one is the low inter-class similarity. That is important. So based on this we can do the clustering. So in this case you can see I am considering these images suppose, and based on this we can do the groupings, but the clustering is subjective. If you see the second figure, you can see if I consider the family, the class will be like this. If I consider the school employees, the class will be like this. If I consider only females, then the grouping will be like this. If I only consider males, then the grouping will be like this. So that is why the clustering is subjective. And in this case already I have explained that the feature vector is available, and based on some similarity we have to group these feature vectors. Here you can see I am giving one example. I am considering in the first example I am considering these two images, and I want to find the similarity between these two. So maybe some Euclidean distance measure we can consider for finding the similarity between these two images, and I am getting the similarity score of 0.23. Similarly, in the second case also, if I consider these two cases, the similarity score is 3. Third case, I am considering the similarity between two fingerprints, and the similarity score is 342.7. I can determine, and these values can be normalized. So this is by using the distance measure, I can find the similarity between the patterns. And for this clustering, one popular algorithm is the k-means clustering. The k-means clustering already I have discussed in one of my classes. That image segmentation class I have discussed about the k-means clustering. So for this I have to consider the k number of cluster centers that I can select randomly, and after this what we can consider, decide the class membership of the n objects by assigning them to the nearest class center. So for this, by measuring the distance between the sample points and the cluster center, I can decide that one. So whether that particular sample points belong to a particular cluster, that I can decide based on this distance measure, that is the minimum distance. After this, I have to re-estimate the k cluster centers, I have to re-estimate, and after this, this process I have to repeat again and again. And finally, what will happen? This cluster center will not be moving too much. It will be fixed after some iteration. And corresponding to this, I will be getting the cluster centers corresponding to k number of, or maybe the c number of classes. So pictorially, I can show this algorithm like this. So you can see I am considering some sample points, and I am considering randomly selecting these centroids k1, k2, k3 centroids randomly I am selecting, and after this you can see I am assigning the sample points to a particular centroid based on the distance measure. I can consider the Euclidean distance. So corresponding to this I am getting 3 classes, one is the green, another one is the red, another one is orange. And after this assignment, this cluster center will be moving because I have to recompute the cluster center, that is the centroid. So after recomputing, you can see the k1 is moving, k2 is moving, k3 is moving. So that is I have to recompute the cluster centers, and after recomputing you can see I am getting the new position of k1, k2 and k3. And after this again I have to decide the sample points which will belong to a particular centroid. So now you can see this green, suppose this point now belong to the cluster center k1. But if I find the distance between this point and this k1, suppose if I find the distance between this one k1, distance between k2, distance between k3, I have to find the minimum distance. Now in this case the minimum distance will be with k2. So that means that this point should be assigned to the cluster center k2. So that means you can see initially it was the green point, and after this, after finding the distance, you can see this point is assigned to the cluster center k2. And after this again I have to recompute the centroids k1, k2, k3. It will be shifted like this, and this process I have to do iteratively, and finally if there is no significant change of the values of k1, k2, k3, then I have to stop the iteration, and that will be the final position of the centroids belonging to the cluster. So in this case I will be getting the cluster, one cluster is this, another cluster is this, and another cluster is this. So k1, k2, k3. And in this case you can see I have shown the concept of the supervised learning and the unsupervised learning. In case of the supervised learning, we know the class labels, and also we have the training samples for all the classes. And you can see we have the classes like this, duck, duck, not duck, not duck, like this, and we have to go for the supervised learning, and we can do the prediction. That is the supervised learning algorithms. In case of the unsupervised learning, what we can do? We can do the clustering. So this is one cluster, this is one cluster, this is one cluster. Based on some similarity we can do the clustering. Again I am showing this one. So how to do the clustering? So we have the training data set and after this, based on some similarity, we can do the clustering. So you can see, so this is one cluster, this is one cluster. Like this, we have the clusters, the groups. This is about the unsupervised learning. Now I will discuss the concept of the reinforcement learning. So concept is like this. Suppose in some applications, the output of the system is a sequence of actions. In such a case, a single action is not important. So what is important? The important is the policy. That is the sequence of correct actions to reach the goal. And there is no such things as the best action in any intermediate state. So that means in any intermediate state, I cannot say this is the best action. An action is good if it is a part of a good policy. And machine learning program should be able to assess the goodness of the policies and learn from past good action sequences to be able to generate a policy. This is the concept of the reinforcement learning. So briefly I will explain one example. So if I consider the playing of chess, so where a single move by itself is not that important, it is the sequence of right moves that is important. A move is good if it is the part of a good game policy. And another example I can give, in robot navigation, the robot can move in one of a number of directions, and after a number of trial runs, it should learn the correct sequence of actions to reach to the goal state from an initial state. And in this case, it should not hit any of the obstacles. So I have given these two examples. So for this, we can apply reinforcement learning. So one action is not important, the group of actions or the policy is more important. That is the main concept of the reinforcement learning. After this, the next concept is semi-supervised learning. Semi-supervised learning is a class of supervised learning tasks and techniques that also make use of unlabeled data for training. Typically, a small amount of labeled data with a large amount of unlabeled data. So that means in case of the semi-supervised learning, we have small amount of the labeled data, and also we have the large amount of unlabeled data. So that is, it is in between the supervised learning and the unsupervised learning. Next concept of the regression. Regression means, you can see, similar to curve fitting problem to a set of sample points. So here I am considering some sample points and I am fitting a curve. So you can see in the figure, first figure and the second figure, I am doing the regression. That is, it is similar to curve fitting problem to a set of sample points. And briefly I can say the linear regression is a statistical method that allows us to model a relationship between a dependent variable and one or more independent variables. And this can be done by fitting a linear equation to the observed data. So that is the definition of regression. So it is a statistical method that allows us to model the relationship between a dependent variable and one or more independent variables. Suppose I can give one example. Suppose we want a system so that it can predict the price of a used car. What I am considering, the price of a used car, that I am considering. So what are the inputs? So inputs are the car attributes. So what are the attributes? I can consider, suppose, brain. Brain is one attribute. Maybe the year of manufacturing, that I can consider, or maybe I can consider engine capacity. Engine capacity I can consider, or maybe I can consider the mileage. I can consider, or maybe some other information I can consider. So based on these attributes, I can determine the price of a used car. So the output is the price of the car. So output will be the price of the car. So this is the regression problem. So briefly I have explained the concept of the regression. So it is a statistical method that allows us to model the relationship between a dependent variable and one or more independent variables. And this can be done by fitting a linear equation to the observed data. So here you can see I am considering some observed data and I am fitting a curve. Next I am considering the classifier. So in this example you can see I am considering a feature space, the two-dimensional feature space. So x1 and x2 I am considering the features, and you can see I am considering two classes. One is the red class, another one is the green class, and corresponding to this you can see the decision boundary between the classes. So this is one example of a classifier that already I have explained in my last class. And one is the empirical risk minimization. So based on this principle, that one is the probability of the error I can determine. So in my next class I will define what is the probability of error. Probability of error I can determine. And another one is the risks. So these are two techniques. By using this we can take a particular classification decision. So we can determine probability of error and also we can determine risks. So risks means suppose if I consider a particular action, corresponding to this particular action I can consider a risks. So this conditional risks I can determine, and based on this conditional risks I can take a classification decision. So that is the empirical risk minimization. So I have to minimize the risks. And one is that no free lunch theorem. What is the meaning of this? So it is impossible to get nothing for something. The meaning is that in view of the no free lunch theorem, it seems that one cannot hope for a classifier that would perform based on all possible problems that one could imagine. That means suppose if I consider one classification algorithm that may be suitable for a particular application, but that may not be suitable for many other applications. So it cannot be generalized. Okay, so that is the concept of the no free lunch theorem. And classifier taxonomy. So there are two types of classifiers. One is the generative classifiers, another one is the discriminative classifiers. So first I will discuss about the generative classifiers. In case of the generative classifiers, we have two categories. One is the parametric classifier, another one is the non-parametric classifier. So let us see what is the generative classifier. So in case of the generative classifier, samples of training data of a class assumed to come from a probability density function. That is the class conditional PDF. So if you remember that in case of the Bayes theorem, we have shown like this, the probability of Wj given x that I want to determine is equal to probability of x Wj, and the prior is probability of Wj, and this is the evidence. So evidence has no role in classification, so it is simply a normalizing factor. Now suppose this is the class conditional density, the class conditional PDF. So suppose the density from is known. Density from is known. So that means density from maybe it is the uniform density, Gaussian density, like this we can consider. And in this case, if I know the density from, we can determine the parameters. Suppose if I consider the Gaussian distribution, in case of the Gaussian distribution, I have two parameters. One is the mean, another one is the variance. So that I can determine if I know the density from. So based on this class conditional density, because if I know the density from, then based on this I can take a classification decision, because if I want to determine this, the probability of Wj given x, I have to know the probability of x given Wj, and also I have to know the prior probability. So by using the Bayes law you get this one, and if the density from is known, that is the density from of the likelihood, this is the likelihood is known, then it is called the generative classifiers. And sometimes the density from may not be available, so then in this case we have to estimate the density. So there are two cases. The first case is the density from is known and we have to estimate the parameters. So this is the first case. The second case is density from is not known. Density from is not available or not known. Then in this case we have to estimate the parameters. In the first case, number one, the density from is known and we have to estimate the parameters. The parameters may be mean and the variance, or if I consider high dimensional case, that will be the mean vector, and also I have to consider covariance. And in the second case, the density from is not available, so we have to estimate the density. So first I will consider the parametric classifier. So what is the parametric classifier? The parametric classifier means the density from is known and we have to estimate the parameters. So that is the parametric classifier. In case of the non-parametric classifier, density from is not known, then we have to estimate the density. That is called non-parametric classifier. In case of the parametric classifier, we know this PDF, the probability of x given W1, that is the likelihood we know, and similarly we know the probability of x given W2, that is also available. So from this we can take the classification decision. So this is about the parametric classifier, that is the density from is known. So in this case you can see I am considering one generative classifier, and you can see the two classes I am considering. One is the salmon, another one is the sea bass. Two types of fishes I am considering, and I am considering two features. One is the lightness of the fish, another one is the weight of the fish, and you can see the decision boundary between the classes. So this is my decision boundary. In case of the generative classifier, so already I have mentioned that one is the parametric approach, another one is the non-parametric approach. In parametric approach, the density from is available, but we have to estimate the parameters. In case of the non-parametric, the density from is not known, but we have to estimate the densities. So you can see here, one is the non-parametric approach. So that means, so from the training samples, we have to estimate the density. Density of what? The density of this. So we have to estimate this density, that we have to determine. This is about the generative classifiers. In case of the discriminative classifier, so no such assumption of data being drawn from an underlying PDF. That is not important. That is, the class conditional density is not important. But what is important, that is it models the decision boundary by adapting the gradient descent techniques. So we can determine the decision boundary by considering one technique, that is the gradient descent techniques. So we can find the decision boundary. So what is the discriminative classifier? Start with initial weights that define the decision surface. So first I have to consider initial weights that define the decision surface. After this, I have to update the weights based on some optimization criterion that we can consider. And in this case, no need to model the distribution of samples of a given class. That is, the class conditional density is not important. What is not important? So this is not important in this case of the discriminative classifier. So this is not important. So some examples of the discriminative classifiers are neural networks like multi-layer perception, single layer perceptions, support vector machines, are some examples of discriminative classifiers. So you can see, first I am considering some initial weights, and after this I am adjusting the weights, I am determining the weights to find the best possible decision boundary between the classes. So in this example I am showing two classes, one class is 1 and another class is 0. So between these two classes I want to find the decision boundary. So first I am considering one initial decision boundary. Corresponding to this I have the weights, but I have to adjust the weights so that I can find the best decision boundary between the classes. And you can see in case of the discriminative classifier we have linearly separable data and also we have non-linearly separable data. So in this example you can see I can draw the decision boundary between the classes. So I have two classes, one is the plus, another one is the minus. So between this I can easily draw the decision boundary, and similarly in the second figure also I have two classes, and between this I can easily draw the decision boundary. So that is why this is the linearly separable data. And corresponding to this linearly separable data, if I consider this one, this equation W1 x1 plus W2 x2 plus B is greater than 0, the B is the bias, W1 W2 are the weights, and x1 x2 are the features I am considering. It's a two-dimensional feature space I am considering, and you can see this is the decision boundary. Decision boundary. So what is the equation of the separating line? The equation of the separating line is W1 x1 plus W2 x2 plus B is equal to 0. And if I consider this green class, corresponding to this green class, the equation will be W1 x1 plus W2 x2 plus B less than 0. That is the inequality. And similarly for the red class, the equation is W1 x1 plus W2 x2 plus B is greater than 0. So based on this formulation, I can distinguish these two classes. One is the red class, another one is the green class. And also you can see the equation of the separating line between the classes. If you see this example, again I am considering two classes. One is the blue class, another one is the red class, that is the plus and the minus. And in this case, it is very difficult to draw the decision boundary, the linear decision boundary between the classes. So that is why I am considering one boundary is like this, another boundary is like this. So by using these two boundaries, I am separating these two classes. So that is why I can say it is a non-linearly separable data. Previously I have shown the linearly separable data, but this is one example of non-linearly separable data. And one important theorem is the Kovar's theorem. So what is the Kovar's theorem? The theorem states that given a set of training data that is not linearly separable, one can transform it into a training set that is linearly separable by mapping it into a possible high dimensional space via some nonlinear transformation. So that concept I am explaining in my next slide. So what is the importance of the Kovar's theorem? So here you can see in the first figure, figure A, I am considering some sample points of the original data that is in 2D, in two-dimensional, which is not linearly separable. So what we can do, I can apply some nonlinear transformation. So nonlinear transformation is applied so that this original data can be mapped into high dimensional space. So if you see the original data, that is the two-dimensional space, but after this transformation I am considering the three-dimensional space, that is the high dimensional case I am considering. So in high dimensional case, these samples will be linearly separable. So that means in 2D it was not linearly separable, but in the 3D it is linearly separable. So that is the concept of the Kovar's theorem. For pattern classification problem, I have to consider some evaluation metric. So one is like this. Suppose we have the predicted class and we have the actual class. So actual class is yes and the predicted class is yes. That means it is the true positive. If the actual class is suppose no and the predicted class is yes, that is false positive. If the actual class is yes and the predicted class is no, then it is false negative. And similarly, true negative I can determine. So one is the actual class, another one is the predicted class. So these parameters, one is the true positive, another one is the false negative, one is the true negative, and the false negative I can determine from the actual class and the predicted class. And these parameters are generally used in case of the pattern classification problem. One is the true positive, the false negative, false positive, true negative, and the true positive rate also you can determine. That is nothing but Tp divided by Tp plus Fn. So that is the true positive rate. False positive rate also you can determine, Fp divided by Fp plus Tn. That also you can determine. Accuracy also you can determine, Tp plus Tn divided by Tp plus Fn plus Fp plus Tn. That also you can determine. And these are some important parameters. One is the precision. Precision is nothing but Tp divided by Tp plus Fp. And also you can determine recall, and the specificity also you can determine. So these are the parameters. And one thing is that you can determine the ROC, the region of convergence, also you can determine. It is the, you can see the ROC curve showing TPR against FPR for a particular pattern matching algorithm. So I am showing the TPR, that is the true positive rate, and FPR I am showing, and you can see the ROC. ROC you can see. So you can see in the second figure what I am showing, the distribution of positive and negative matches I am considering. That means the true positive and the true negative I have shown, which is shown as a function of interfeature distance. The interfeature distance is d. So you can see I am getting the Fp and Fn also, that is the false positive and the false negative, and you can see the threshold I am considering. So based on this threshold you can determine the true positive and the true negative. And finally I want to show another important metric, that is called the confusion matrix. Confusion matrix. So this is used to show the performance of a pattern classification algorithm. So in this example you can see I am considering actual class labels, and also you can see the number of test patterns assigned to different classes. So what is the meaning of 137? That means this, suppose the class, suppose the pattern 1 is recognized as 1, how many times? 137 times. The pattern is recognized, the pattern 1 is recognized as 2, 13 times. The pattern 1 is recognized as 3, 3 times. So like this I can determine the confusion matrix, and from this you can see, from this you can determine the accuracy, you can determine, and also you can determine the misclassification rate also you can determine, and also you can determine the rejection rate. Rejection rate means how many times it is not recognized as 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose I am drawing a character, suppose like this. So it is not recognized as 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is why it is not recognized. So from this I can determine the rejection rate. Similarly, what is 55? That means 2 is recognized as 2, how many times? 55 times. The 2 is recognized as 1, how many times? 1. That is the misclassification. That is the misclassification. And 2 is recognized as 3, so how many times? It is 1 time. So that is the misclassification. And you can see from this information I can determine the accuracy. So in the confusion matrix I will be getting a diagonal matrix. So I will be getting the diagonal matrix. If I get the high values in the diagonal matrix, that corresponds to the high accuracy of the pattern classification algorithm. In this class I discussed the concept of pattern classification. I discussed the concept of supervised and unsupervised learning. After this, briefly I have highlighted the concept of semi-supervised learning and the reinforcement learning. After this, I discussed the concept of generative classifier and the discriminative classifier. So let me stop here today. Thank you.